Hello, everyone. Welcome back to today's lecture. Today, we're going to talk about the inverse voting game. Following from the last lecture, where we distinguished the direct and the inverse voting games, we established that the settings and the models are very similar in both games, and what differs are what is given as the exogenous variables and what are the endogenous variables. Namely, what are given and which variables are to be discovered. So we can say they are using the same mechanism, but in the opposite direction. Today, we'll be focusing on the inverse voting game. So our choices will be given. We want to find the network weight. Remind that the networks are weighted and there can be friends or enemies, as, as well as the threshold. We discussed about the choice of making thresholds both endogenous in the previous lectures, and for the inverse voting game, these are the given and these are the to be found variables, and we are focusing on network discovery application. So the mechanism of vote is whether the weighting sum is greater than the threshold. Let's go and look at the next slide. So why are we caring about network discovery? Because in several applications that comes naturally, we often observe the outcomes, but we cannot directly influence and measure who are the influencers of these outcomes, if there exist any. For instance, in the school settings where students are affecting each other in an implicit way, how does the consumptions of some substances affecting between individuals? In this case, we know the friendship or the link between the students. We know which students are in the same class, how close are they in terms of geological locations, but we don't know about how true influence link are uh, presented between those students. Another example, when we got firm product decisions, we got the market data, they are observable, but whether they are imitating or differentiating themselves from the other companies in the strategic settings, it is unknown. So it is to be discovered. In the country vote at the United Nations, the voting records are public. We note the voting results, but the underlying alliances pressures, we don't know about that. So all these examples says that the inverse voting games try to recover the signed weighted network that best rationalize with the observed choices under this voting mechanism. So let's look at how our settings. Let me show you the examples before. Let's say we got an individual I, and individual I have some neighbors, J1 and J2. We know who are our neighbors, but we don't know whether they are friends or enemies. So they can be a friend, they can be an enemy, we don't know about that. And also we don't know about the weight. So as opposed to direct voting settings, these two variables are now unknown, are now endogenous. For the sake of implementation convenience, instead of introducing the weight between ij and an indicator whether I is friend with j or I is enemy with j, we decide to combine those variables. So we introduce the variable weight with the with the overline and an underscore. So overline means the weight if I and J are friends. So I is friend with J. In this case, we note with W over line. And on the other hand, if I is enemy with J, we use underscore wij. So normally, um, two individuals cannot be friends and enemies at the same time. So one of them should be zero. So, and yeah, at least one of them should be zero. And also, if I and J are not friends, so let's say J3 is not a friend of I or not connected to I, then both W overline and W underscore between those two individuals should be zero. So these are the possible constraints, the three constraints that established this relationship. The third constraint says that the threshold is bounded by total weight. This is a convenient constraint for our mixed integer linear programming implementations so that we got a upper bound for our threshold. So in this case, the weighted sum becomes this expression. Before, this weighted sum is only summing on friends, and this summing only on enemies. But since now W overline is only non-zero for friends and W underscore is only non-zero for enemies, we can just sum up for all the neighborhood of I. Actually, you can sum up for all the whole network because we established that if they are not neighbors, then the weight is zero. So we're just adding a terms of zeros, which doesn't affect the weighted sum result. And this will simplify the way we express the weighted sum. So one thing to notice is that, let me draw the diagram once again. So Yij, J1, and J2. Since we're calculating the weighted sum based on the choices of neighbors, but since the choice are fixed, the weighted sum actually does not depend on the choice of J. Let me explain. So the strategic choice of I is how should I distribute the weight between his neighbors, right? So his choice about how to choose whether to assign some neighbor as friends, assign some neighbors as enemies, does not depend on how J1 assign his neighborhood. So the strategic choices of J1. So in this case, the strategic choice of I does not depend on the strategic choice of all the other individuals. In technical terms, the game is now separable. There's no strategic interaction between the individuals. This is the property of the inverse voting game. So the consequence is that every social welfare solution, every solution where you maximize the whole utility of everyone is also a Nash equilibrium because they are not interacting with each other in the strategic settings. So we can solve this utility just by solving independently for each individuals. So structurally speaking, the inverse voting game is simpler than the direct voting game. And now let's look at some property of the best responses of the inverse voting game. So let me draw some diagrams. Notice that the features are chosen, are fixed. So let's say we got feature F1 and feature F2. So let's say individual J1 chooses all 1, individual J2 choose all 0, and individual I choose differently. In this case, since I is taking weighted sum of their neighbors, we know that the weighted sum of individual I for feature F1 is always the same as weighted sum of feature F2 because taking from the choices of neighbors, they always be the same. The neighbors always vote the same for feature F1 and F2. So this is what it says. So if feature F1 and F2 are chosen differently, here I choose 1 and 0 for both features, but all the neighbors of I choose them identically. So here, all the neighbors of I choose the feature F1, either they both choose them or they both not choose them. In this case, the weighted sum will be the same for both features. However, um, in order to fit into the perfect response, the best response, I cannot score the utility for both features. Because why? Let's say I chooses any threshold, right? So there are either both greater than thresholds, making I always suggested to vote 1, or they can be smaller than the threshold, suggesting all vote 0. But in any case, there cannot be a perfect match. So in this case, in the first case, um, let's say the weighted sum is greater than the threshold, then the suggested vote for the second item, second features, will be not perfect because I is choosing 0, but the neighborhood suggests to be 1. So in this case, you don't get a perfect um, social welfare solution. And on the other hand, if I choose a threshold smaller than the weighted sum, then it will both suggest to be voting 0. In this case, the first feature will be not a perfect social welfare solution, meaning that the perfect fit is impossible in this case. So whenever this situation happens, we know for sure that the ultimate social welfare solution cannot be perfect. Equals F means every feature is satisfying this criteria. Let's look at the second proposition. So we say that if the weighted sum cannot be separated from some features, then it is smaller than F. Actually, let's look at the third one. It's a bit easier to understand. So that's again, we got individual I, J1, and J2. Okay? Let's say I chooses W in such a way. Let's say I vote, now we got feature F1, F2, and F3. Let's say in this case, and F1 is voting 1, F2, 1, F3, 0. So I chooses feature 1, I chooses feature 2, and I doesn't choose feature 3. And we got the choices for J, choices for J. Yes. So let's say we calculate the weighted sum. Once we decide the weight, so we got the weighted sum for feature 1, weighted sum for feature 2, and weighted sum for feature 3, right? So we separate in two groups. We separate the groups for which I chooses that feature. So in this case, if we want a perfect utility contribution, we should make it greater than the threshold. We should make it greater than the threshold. Then we'll be very happy about that. On the other hand, the other group is the group of 0. In this case, we want the weighted sum to be smaller than the threshold. Let's say this situation can happen. Let's say this situation can happen. Then for the first feature, we suggest to vote 1. For the second feature, suggest to vote 1. And the third features, we suggest to vote 0. We notice that this is always a perfect match. So utility equals F. Utilities equals half. And what is the sufficient condition for this to happen? Well, how can it happen? So this weighted sum should be greater than a threshold, and this weighted sum should be smaller than the threshold. How can it happen? Well, if the minimum of this is greater than the maximum of the second group, we agree that if this happens, all the maximums of the weighted sums, let me do it this way. So the weighted sum of the first group have these numbers, and the weighted sum of the second group has this number. If we take the minimum of one and the maximum of the other, and then we got this relationship, the minimum of the first group is greater than the maximum of the second group, then what you can do is you choose the threshold here. So the threshold is always greater than the green group and always it will be always smaller than the green group and always greater than the red group, so that you can make the classification perfect. On the other hand, if this doesn't happen, we know that there must be at least one feature that doesn't perfectly match this. So the second proposition is the inverse case. If this cannot happen, then our utility is cannot is smaller than f, so not perfect. So the takeaway is the condition 3 and also the condition 2 is the linear separability condition. If it can be separated, as I illustrated earlier, then we can have a perfect classification. So how can we use inverse voting game as a network discovery tool? What inverse voting game recovers is which edges are attractive, which edges are repulsive, also the strengths of each link between individuals, and our output will be the graph. So as the network discovery tool, we input what are the choices of individuals and we output the link between them, who are imitating which individuals and who are trying to differentiating themselves from other individuals. So for the application preview, we will talk about our applications in lecture 10, where we apply the inverse voting games to a data where we got 129 school students and different features for the substance consumptions. The recovered network will be close to the observed friendship network, but there are some differences between them, and we will talk about them in the following lectures. In summary, inverse voting games is, as the name suggests, inverts what is from the direct voting game in terms of which variables are fixed, which variables are going to be discovered. Second point is that the game is a separable game. There are no strategic interaction between individuals, so the Nash equilibrium is the social welfare solution. The third point is we got a sufficient condition for the perfect fit. If there is a linear separability conditions on the weighted sum, then this perfect fit can happen. The fourth point, structurally speaking, the inverse voting game is simpler than the direct voting game, but it is also a powerful tool for the discovery or network discovery application. Thanks for watching for today's lectures and see you guys in the next one. Bye bye.